Hello students. In this lesson, we will study some theorems about zeros of polynomials, and it turns out that the zeros of polynomials are related to polynomial division, one specific type of polynomial division which we will talk about, and some theorems, some results related to these concepts. Let us begin with the intermediate value theorem. You can see the statement of the theorem on the left side, and there is a graph on the right side. I will illustrate the concept with that graph. The idea of the theorem is very, very simple, okay? Which is, if the polynomial goes from a positive value, let's say, to a negative value, I'm talking about the y values, okay? The y value, the value of the polynomial, which is the y coordinate, is going from positive to negative, right? If that happens, the theorem says there must be a point somewhere in between where the value was zero. You would say obvious, right? If you go from positive to negative, you must get a zero somewhere. In the same way, if you go from negative to positive, so if you go from a negative value here to a, let's say, some positive value here, there must be a point in between where it is zero. So, in general, we say if they have opposite signs, if P of A and P of B have opposite signs, then there is a zero in between. Now, what is a zero? Where the polynomial takes value zero, that is the x-intercept, right? There is an x-intercept in between those 2 points. Now, only important thing I will note here, why is such an obvious fact a theorem? Because such a fact is true only for continuous functions. Okay. Now, we are not getting into the calculus type of continuous functions here, but in college algebra, we have understood the concept of continuity to be something that you can draw without lifting your pen, right? Continuously. So if it is continuous, then this statement is true. And polynomials are continuous functions. Okay. Hence, that theorem applies. Let us look at a concrete example with this graph. At a equals 2 and b equals 4, what are the values? F of 2 is here and the point is down here. So at 2, the value of the polynomial is minus 2, right? And at 4, the value of the polynomial is 1. Okay, so f of 2 is minus 2 and f of 4 is 1, which have opposite signs, right? And because they have opposite signs, the intermediate value theorem ensures there is a zero between them. Okay. And we can see that we have already noted that zero is there. Okay. We can also deduce this analytically by choosing A and B appropriately. Okay, I should not say this. I would say such information. Okay. Now, in this particular case, we had a graph and it was visually very easy to find a value where it is negative and a value where it is positive, right? But suppose you are given a polynomial and not a graph, okay? You have the analytic, the equation of the polynomial. In that case, what you can do is we can go on, you have to do some hit and trial, okay? You can test with some different values of A and B until you find a value where it is positive and a value where it is negative. Then you know that in between them there is a zero. So let us work out this example here. This polynomial p of x I will evaluate at half and 1. Okay, so 3 times half cubed plus 7 times half squared minus 4. And go ahead and evaluate that. You can use a calculator or do it mentally, which is quite easy here. 3 over 8 plus 7 over 4 minus 4. And you can work that out. Okay, it will be 3 plus 14, 17 minus 32. That is minus 15 over 8. Okay, so that's a negative value. And if you plug in 1, you get 3. 1 cube will be 1 plus 7 times 1 square will be 1 minus 4. 10 minus 4, which is 6. Now we have this 15 over 8, which is less than 0, minus 15 over 8 less than 0, and 6 greater than 0, right? Therefore, you can now write your conclusion by intermediate value theorem. There exists a 0 of u of x in the interval half to 1. And I can use parenthesis because it's not half, where it is negative. It's not 1 where it is positive. It's in between, right? So in that open interval, there is a 0 of the polynomial. Just appreciate how powerful this conclusion is. Like, between half and 1 is quite a narrow interval. Okay, within that narrow interval, there is a 0 of the polynomial. You are able to, say something quite strong here. Okay, and observe this. Both in the case of the graph, where we had that 0, marked by that blue circle there, and in this second example where we said there is a 0 between half and 1, we never said what is the value of the 0, right? And that is the thing about intermediate value theorem. The intermediate value theorem only guarantees the existence of a 0. Okay, it does not give the 0. It only guarantees the existence of a 0. To find the zeros, we will need other results, other theorems, which we will be talking about. Okay. Now, proceeding in that direction of results that we need for finding zeros and theorems, we will begin with synthetic division. Now, in the introduction, I was talking about we are going to be doing some particular type of polynomial division, okay, which is this. We are going to develop this technique of performing polynomial division where the divider is a linear polynomial, and even in linear a specific type with coefficient 1. Okay, it's like 1x plus some constant. Okay, that specific type of polynomial divider of this type. Okay, so that is going to be the divider, and the polynomial could be any polynomial. So specifically, we are not going to divide by some higher degree polynomial. We are not dividing by a quadratic or cubic polynomial. Okay, any polynomial dividing by a linear polynomial. And then synthetic division is a method which applies to that. How is it performed? Follow me for the first two examples at least. Okay, you make this small table. In fact, let me drag this a little bit down, where you write the coefficients of the polynomial. Okay, now the thing about synthetic division is, as the word suggests, synthetic, we're trying to do something in a faster way, something more efficient than doing the regular polynomial division. Okay, so we deal with only the structure, main skeleton of the polynomial, that is the coefficients. I'm going to list the coefficients. 1x to the 4 plus 4x cube plus 2x square plus 9x plus 4. Okay, only the coefficients in the descending order. And the divider is x plus 4, right? And you write minus 4 here. Think about it, it's going to be what is a possible zero. We don't know whether that 4 minus 4 is a zero or not. It's a candidate, right? It's a possible zero. Because if you set x plus 4 equal to 0, you get x equals minus 4. So always think like that. Okay. So when you have plus here, you take minus, in the synthetic division. If you have a minus sign there, then you take the plus value. So basically you set the divider equal to 0, and what value of x you get there, that is written here. Okay. And once you do that, you draw one more small line here. I will talk about that in a while later. Now the synthetic division begins. Okay. And it is a very simple process which in which there is one particular step, and we repeat that step again and again. The step is this. First we write 0. Okay, that is like the seed. We begin with that. Then we add the two numbers. 1 and 0 gives you 1. 1 plus 0. And then we multiply minus 4. Okay, we multiply this minus 4 with that number in the lower row. Minus 4 times 1, minus 4. Then we add that 4 and minus 4, you get 0. Then you multiply the minus 4 with 0, you have 0 here. You add 2 and 0, you get 2. Multiply the minus 4 with 2, you have minus 8. You add the 9 and minus 8, you get 1. You multiply the minus 4 with 1, you get minus 4. You add 4 and minus 4, you get 0. Okay, this is the process. And in this process, we obtain everything. Okay. The sequence of numbers that you get here, those will be the quotient. Okay, they give you the quotient, right? When you divide a polynomial, there is a dividend, there is a divisor, then on the result side, there is a quotient, and there is a remainder, right? So the reason I was drawing this line here earlier was this part here is your remainder. Okay. So in this case, the remainder is 0, which means the polynomial exactly divides. Okay, x plus 4 divides that polynomial exactly. And you can write your conclusion like this. P of x, that polynomial, is equal to two things. Okay, let's say I write the divisor first. That is x plus 4, which is the divisor, times, okay, I'm writing below here, but I'm multiplying those two factors there. X plus 4 times the quotient, right? The quotient has coefficients 1, 0, 2, 1. So how do I begin the polynomial? The original polynomial is x to the 4. You start with x cube now because you are dividing by x plus 4, right? Degree 4 is divided by degree 1. So the quotient is degree 3, 1 less. So x cube, that is 1x cube plus 0x square plus 2x plus 1. Okay. And normally it is quotient times the divisor times quotient, or quotient times divisor plus the remainder, which in this case is 0. Okay. So that means x plus 4 is a factor of that polynomial, or you can say minus 4 is a 0 of that polynomial. Okay. Let us perform one more. If you are feeling confident, you can go ahead and do it before I do it, and you can verify your solution with me. But otherwise, no harm. You can follow me for the second example. Okay. Okay. Hopefully you did not lose much here. I was talking about setting up the synthetic division for the second problem. Okay. Now again, you are dividing by x plus half. So you write minus half here. Then you write the coefficients of the polynomial, right? Which is minus 3. That is x cube. Then x square is missing. So you have a 0 there. Okay. Minus 1x minus 5. So that is another thing that you have to be aware of and conscious. Okay. When you write those coefficients, you have to make sure you start with the highest degree, the leading term, leading coefficient, and write in the descending order. If any exponent is missing, like x square, or any term is missing, it is actually 0x square. Okay. So you write 0 in the coefficient. So you don't, in your coefficients that you write, you should not miss any exponent of x. You have to write 0 if you don't see it in the polynomial. Okay. And let us start our process now. First, we write 0 for the leading coefficient. Then you begin. Minus 3 plus 0, minus 3. Minus half times minus 3. 3 over 2. 0 plus 3 over 2. You get 3 over 2. Minus half times minus 3 over 2. You get minus 3 over 4. Minus 1 minus 3 over 4. You have to add them, So both are negative. So you add the numbers 1 plus 3 over 4, which is 7 over 4 with the minus sign. Then negative half times negative 7 over 4. You get 7 over 8. Okay. And now you add them, you get negative 40 plus 7, negative 33 over 8. Okay. So the polynomial division has been performed and your result is this. That polynomial p of x is equal to, let me write the quotient first. Okay. The polynomial is a cube, right? So you start with x squared minus 3x squared plus 3 over 2x minus 7 over 4 is the quotient times x plus half is your divisor and remainder is minus 33 over 8. Okay. That is synthetic division. Okay. There is a reason we studied the synthetic division. We will be using it extensively. Okay. Next, we will use this, in the remainder theorem, factor theorem, things that are going to come up. Now, in the synthetic division, we said that, the last number that you get here below the constant is the remainder when that polynomial is divided by that linear polynomial, right? And synthetic division also gives you the quotient. Let us say you are interested only in finding the remainder. Okay, and there are reasons why sometimes you might be interested like that. For example, if you want to know whether a number is a zero of the polynomial or not, or whether you want to know if a linear polynomial is a factor of the polynomial or not. In that case, if you get the remainder that is obtained by when you do the polynomial division, if the remainder is 0, then it's a factor, right? And if the remainder is not 0, it's not a factor. I'm just giving one example. And there are other reasons. Sometimes you might just want to know what the remainder is when you do the division, but you don't necessarily need to know the quotient. Okay. In that case, it would be better if we had a more efficient method, right? Which is given by the remainder theorem. What does it say? When this polynomial px is divided by this linear polynomial x minus k, the remainder is p of k. Okay, which means you evaluate the polynomial by plugging in k in place of x. The value that you get will be the remainder if that polynomial is divided by x minus k. Very interesting theorem. Okay, so let us look at an example. Suppose the polynomial is that and the value of k is square root of 3. Let us first compute p of k. So it will be under root 3 to the power 4 plus 2 times under root 3 squared minus 10. Now, under root 3 to the power 4 can be written as squared squared, right? Laws of exponents. And under root 3 squared, the root and the square will cancel. So you get 2 times 3 minus 10. Okay, so I mean, you have to be clear that, this under root 3 squared that I wrote here, that square applies only to under root 3, to x squared. And so now you have under root 3 squared is 3. So 3 square is then 9. 9 plus 6 minus 10. That is 50. Okay. No, no, not, I mean, sorry, 15 minus 10, which is 5. So the second question now is, what is the remainder if that polynomial was divided by this linear polynomial x minus root 3? And the answer we know is now 5, right? Which is p of k. That is what the remainder theorem says. When you evaluate the polynomial for that value of k, you get the remainder. Okay. So no synthetic division, we directly got the remainder. You want to verify, right? You can go ahead and do the synthetic division. Let us see. It's a fun exercise. I'm only doing this so that we will verify that that is in fact the remainder. Okay. And also, it's a good practice for computing the performing the synthetic division. K is root 3 here. You are dividing by x minus root 3. Okay, so the value of k is root 3, which is what you write in the synthetic division as the divider. Now write the coefficients in the descending order. 1x to the 4, 0x cube, 2x square, 0x, okay, that is important, minus 10. Draw the line there. We'll see what the remainder is. First write 0, 1 plus 0, 1, root 3 times 1, root 3, 0 plus root 3, root 3, root 3 times root 3, 3, 2 plus 3, 5, root 3 times 5, 5 root 3, 0 plus 5 root 3, 5 root 3, root 3 times 5 root 3. Now you multiply the root 3 and root 3. That is 3. 5 times 3 is 15. Okay, you can do it on the side or do it mentally. Minus 10 plus 15, 5, which is the remainder. Okay, so you can see that remainder theorem gives you the accurate remainder. Okay. Factor theorem is a small result that follows from the remainder theorem. In mathematics, we call them corollary. Okay, you might want to know that word, for general knowledge. It's a corollary of the remainder theorem. Okay, what does it say? If a linear polynomial x minus k is a factor of a polynomial p of x, then p of k is 0. But we have just studied the remainder theorem, right? The p of k is the remainder. So if the remainder, if you divide a polynomial by another polynomial and the remainder is 0, then it is a factor, right? That is the definition. And in that sense, factor theorem is only, taking the statement of the remainder theorem, which says that the remainder is p of k. Now you are saying if that p of k is 0, that is the remainder is 0, then that x minus k is a factor. Okay, hence this is a corollary of the remainder theorem. Okay, that's one thing. The other thing is, please note the word if here. Okay, that's not a typo. You might already know it. If you didn't know, the if stands for, okay, is equivalent to, this is how I'll write it, stands for if and only if. Okay, which means that statement is true in both directions. If x minus k is a factor of px, then p of k will be equal to 0, and vice versa. Or conversely, if p of k is equal to 0, then x minus k is a factor of p of x. Okay. In such cases, when it is true in both directions, we write the word if. Okay. Let us use the factor theorem to determine if x minus 2 is a factor of that. Okay. So what do we need to do? We need to compute p of 2. The polynomial is simply stated like that. So I'm going to say let p of x equal to that polynomial, x cubed minus 3x squared minus 13x plus 28. Then I can compute p of 2, which will be 8 minus 3 times 4, 12, minus 13 times 2, 26, plus 28. And if you simplify, 8 plus 28 is 36, minus 38, which I know is not 0. That's all I'm interested in. It is not 0. This implies x minus 2 is not a factor of that polynomial p of x. Okay. Moving on. Use synthetic division to determine if, now we are doing practice problems on the two theorems and the synthetic division that we just studied. Okay. Use synthetic division to determine whether the given number is a 0 of the polynomial. Now this is only a restatement of, like, asking, it's a restatement of the factor theorem, the question. Okay. Because if the given number is a 0, then x minus that number will be a factor. If k is a 0, x minus k is a factor. So this is like asking, is x minus k a factor of that polynomial, essentially. Okay. And how do we do? It says do it by using synthetic division, and the process is simple. You can go ahead and do it and then verify with me. Okay. Write the polynomial in the descending order. And perform the synthetic division. Okay, you can check your work now. And the remainder here is not equal to 0, correct? And the conclusion you can draw here, conclusion is 5 is not a 0. Okay, and not the question is not asking, but if you wanted to, for your own satisfaction, if you wanted to write out how exactly that 5 is related to the polynomial, you can write this. That polynomial p of x, which is x square plus 4x minus 5, is equal to, divided by number 5, right? Which is the factor x minus 5. And the quotient that you got is 1 and 9. So that is x plus 9. Okay. And the remainder is 40. So you can say plus 40. Okay. The next problem, again, please go ahead and solve it by yourself first and then check with me. Minus 4 is the value of k. The polynomial is 9, 39, 12. And if you did the problem first by yourself, you may have missed this. I hope you did not. There should be a 0 there. So we have to go in the descending order, but we have to reach until you have a constant term. Okay, x cube, x square, x, and then constant. Actually, it is about the exponents. The exponents are x cube, that is 3, x square, that is 2, x, that is x to the 1, and then you should have x to the 0, right, which is constant. Okay, so you write in the descending order until you reach the exponent 0, which is constant number. And I will show you that that becomes important when you want to write the the quotient of the after the division process. Okay, let us continue now with the division. First you write 0, 9 plus 0, 9, minus 36, get 3 here, minus 12, get 0, get 0, get 0. So you might say that it doesn't matter. I already had the same 0 before also, but it will matter when you want to write the quotient. Okay. First, our conclusion. Okay, before getting into other things, what the question is asking. The question is asking if that number is a 0 of the polynomial, and the remainder we get here is 0. Okay. So the conclusion is minus 4 is a 0 of p of x. And then you can write more strongly. I will write that in fact. Okay, p of x, which is that cubic polynomial, 9x cubed plus 39x squared plus 12x is equal to x plus 4, the divisor, times, I'm writing below that. Okay, the quotient will be 9x squared, that is important, plus 3x plus 0. Okay, if you did not do that, if you did not have that last 0 when you wrote the coefficients, you might miswrite the quotient as 9x plus 3, right, which would be incorrect. Okay, all right, moving on. Find other zeros given 1. Okay, so 1 0 of that polynomial is given to you. You need to find the other zeros. Let us see. It's all synthetic division again and again. Okay, so you are getting good practice here. You should do it first by yourself and then check with me. Okay, write down the coefficients in the decreasing order. Zero here, so 1 times 1, 3, 2 plus 3, 5, 15, 4, 12, 0. So first of all, the question is correct. Okay, you have to check that. No, it's a 0. Otherwise, it would not happen, right? Okay. Then what are the other zeros? For that, look at the quotient, which is x square plus 5x plus 4. Okay. And set that equal to 0. Because the divisor is x minus 3. By the way, here, okay, the divisor is x minus 3. So that has given you the 0, 3. The quotient will give you the other zeros. And those will be obtained if you try factoring always first. Okay. And if you give a thought for a few seconds, you'll realize it is x plus 1 times x plus 4, which gives you the zeros minus 1 and minus 1. If you want, you can use the quadratic formula, which sometimes we will be forced to use if you cannot factor it. I have spoken many times about factoring before, so I'm not talking about it now. Okay. All right. Moving on. Same question. There is a polynomial, and you are informed that number 4 is a 0. Find the remaining zeros. Go ahead and do the synthetic division. Minus 1, 4, 7, minus 28. Down. 0 here. Minus 1 plus 0, minus 1. 4 times minus 4, 0. Sorry. I'm thinking ahead. Minus 4. When you add, you get 0. 4 times 0, 0. 7 plus 0, 7. 28. Minus 28 plus 28, 0. Okay. This time you can write it freely. Okay, you don't have to follow one particular way of writing every time. This time I'm going to write like this: that polynomial p of x is equal to minus x square plus 7, right? The quotient. See, the x term is missing. Okay, it's 0. Minus 1x square plus 0x plus 7. And the divisor is x minus 4. Okay. Now what do we want to do? We want to find all the zeros, right? Set it equal to 0. So from this last factor, you get x equals 4, which is already given. The other zeros will come from minus x square plus 7, right? So you write here in the next step. This implies either x is 4 or minus x square plus 7 is equal to 0. And that gives you minus x square equals minus 7. We are solving that equation now. Okay. Cancel the minus sign. X square equals 7. So by using the square root property, you will say it is plus minus root 7, which are the remaining two zeros. Box your answer. Okay. All right. So we saw an example where we could factor the quadratic. We saw a second example where you can solve by, because there is no x term, you can directly solve it by taking the constant to the other side and using the square root property. We will see another type in another example. So I have tried to include every type of example for your practice. Okay. factor into linear factors given that k is a 0. Now, this question sounds different, but it is basically the same question that we were doing before. Okay. If you factor a polynomial into linear factors, that basically gives you the polynomial, zeros, right? So we are doing the same work again, basically. So go ahead and do the synthetic division. 2 minus 3 minus 5, 6. Okay. And we are dividing by 1. 0 here, 2 plus 0, 2. 1 times 2, 2. Minus 1. Minus 1 here. Minus 6 when you add. So it becomes minus 6 here. That gives you 0. So, okay, k equal to 1 is a 0. Now we agree. But what else do we get? We get the quotient function. Let me write as q of x as 2x squared minus x minus 6, which should give you the other two zeros, right? Set it equal to 0. Now, you have two choices. Either factor it or use quadratic formula. Now, if you already know how to factor it, you have learned some particular technique, go ahead and do that. If you feel comfortable using quadratic formula, go ahead and do that. I am going to discuss a method of factoring these kind of quadratics where the main coefficient, the leading coefficient is other than 1. Okay. You might have learned a slightly different variation of the technique that I'm going to talk about. So if you already know, you can go ahead and do your way. Okay. If you do not, then listen to me and follow carefully. The method is this. Okay. There is 2 here and there is minus 6 here, right? Those are your like ax square plus bx plus c. So your a is 2, b is minus 1, c is minus 6. And this method is called AC method. Okay. So what we do in this method is we multiply a and c. You get a times c, 2 times minus 6, that is minus 12. Okay. Now what you want is you want two numbers whose sum. Okay. So the numbers I'm going to write as big A and big B, so it's not confusing. A plus B should give you that middle number, minus 1, which is B. And A times B should give you that AC, which is minus 12. That is the technique. Okay. So this is the sum. And when you multiply these two, whatever you get should be the product. Okay. So figure out the two numbers. When you add, you get minus 1. When you multiply, you get minus 12. So clearly, one number is positive, the other number is negative, right? The product is negative. And the sum is negative 1, which means the bigger number is negative, the smaller number is positive. Few seconds, and then you realize they are minus 4 and 3, right? So A is minus 4, either of them, okay, doesn't matter which one you choose. B is 3. And then what we do, some students know how to directly write the factors after this, okay, but I'm going to follow a little lengthy method in which you split the middle term. That minus x will now be written as minus 4x plus 3x. That is where these numbers come into picture. Okay, minus 4 and 3. So that minus x is minus 4x plus 3x. Minus 6. Now you can pair them up. The first two and the last two. From the first two, we factor out 2x. You have x minus 2. From the last two, you factor out 3. You get x minus 2. So that x minus 2 is now a common factor. You can, observe that this x minus 2 x minus 2. That is your common factor, right? Then what remains? 2x from the first term and 3 from the second term. Okay. Now what we are saying, I should have written implies. Okay, this equal to 0, equal to 0, equal to 0. Okay, x minus 2 times 2x plus 3 equal to 0. That gives you x equals 2 and minus 3 over 2. You can say that. Okay, 2x plus 3 equals 0. You get x equals minus 3 over 2. Those are your other zeros. Okay. Use factor theorem to determine if x plus 1 is a factor of this. This is, as I said, additional practice. So by now you should be very comfortable doing this. Okay. So you say let p of x equals that polynomial. Then you evaluate p at minus 1. Okay. Minus 1 cubed will be minus 1. 6 times minus 1 squared will be plus 1. So plus 6 plus 31, because minus 31 times minus 1. Okay, will be plus 31. Minus 36. Now that is minus 37 plus 37, which is 0. Right? If p of k is equal to 0, this implies x plus 1 is a factor. Okay. All right. So this will be our next lesson. I will make a different video for that, okay, in which we will study some more theorems about polynomials and especially the zeros of the polynomials. I'll see you in the next video.